Greetings to all participants on this webinar. Thank you for joining us. This webinar is going to be titled, How Costly is Your Design? My name is Natarajan. I represent EGS India. We hope you enjoy this presentation. The agenda of this presentation starts with an introduction to EGS India, an overview of the design process, the cost and value paradigm as customers see it, the answers with regard to the design for cost challenges, learning by an example, and we'll summarize the presentation towards the end with question and answers. EGS India was started in 1993 from our US operations, EGS Incorporate USA. EGS became an independent entity in 2003, having 2 branch offices in India in addition to our headquarters in Chennai. Our vision is engineering development through effective partnership with our companies, our customers. We try and achieve the vision by the following mission statements: imparting leading edge technology, training and development, problem solving and new product development through consulting services, and providing software solutions and technical support. The business model of EGS India starts with 3 different verticals: engineering services, software solutions, and technology training. Under engineering services, we provide design engineering services. Under software solutions, we are the authorized reseller of SolidWorks suite of products from Dassault Systems SolidWorks Corporation USA. And under technology training, we provide training through a brand name called Academics on topics such as geometric dimensioning and tolerancing, tolerance stack-up analysis, finite element analysis, failure modes and effects analysis, and many other technology-driven trainings as required by the industry. Under the engineering services, we cover the entire gamut of engineering, design, finite element analysis, and software development, which helps our customer develop products faster in a highly productive manner, getting their first time right as the goals for their products and technologies. First, let us look at the design process overview. Any product that we design is driven by quality objectives. These quality objectives have to be measurable objectives. They can be classified under 2 segments, namely the assembly objectives and the performance objectives. Performance objectives drive the design for life and the performance of the product that we are designing. Design failure modes and effects analysis forms the bedrock of all design processes, starting with the statement of requirement during the design process. The DFMA drives and gets influenced by the performance objectives, while the assembly objectives gets influenced by the DFMA. The assembly objectives are translated into design for assembly objectives. From the design for assembly objectives, we get the datum reference frames for the GD&T drawings. We perform the tolerance analysis and use the cost of precision and cost of poor quality inputs with the design for cost and do the tolerance optimization. The inputs for the tolerance optimization across multiple DFQs comes from your DFMA in terms of the risk priority numbers provided there to classify the criticality into critical, essential, and desirable characteristics, and these get translated into the key characteristics that get put on the GD&T drawing. Design for manufacture with inputs from the process capability CP and CPK forms an input to the GD&T drawing in addition to the design for cost, design for service, design for transportation, so on and so forth. In this presentation, we are going to be concentrating on the cost of poor quality versus the cost of precision, and the design for cost being a driver towards the profitability of the organization. The cost and the value paradigm as seen by the customers and as witnessed by us during the design process or the manufacturing process for a product development is shown here. The first quadrant refers to the robust design practices with performance and the tolerances as the metrics against which it is measured. Quadrant number 2 deals with better marketing and the revenues that comes along with it, while quadrant number 3 is nothing but a linear graph because most of them are cost, both the ordinate and the abscissa. And the fourth quadrant deals with the better manufacturing processes with the manufacturing cost going up as a result of tightening of the tolerances or the clearances. When we look at this graph, we see that for a particular performance, for a manufacturing capability, and with regard to the marketing practices, we can see that the revenue and the cost come on either side as shown by the red lines. The difference between these two results in the profit or reflects on the profit. Now, the choice of performance, the choice of the manufacturing practices, and the positioning of the product drive the profitability. As the revenue comes down and as the cost escalates, the profitability comes under threat. This is a classic analysis of the cost of the product versus the value of the product as perceived by the customer. The direct cost influence factors can be stated as starting with the part factor of safety, the number of parts going into the assembly, the tolerances that have been specified on the parts, the material used in the part definition, the weight of the parts, the manufacturing operations, and the packaging and transportation. These are some of the direct cost influence factors that we see day in and day out, where we get a feel for what they are. The part factor of safety in particular decides the cost of the product at the design stage. For a factor of safety 2.0, you could have a certain cost. For a 2.5, the cost could be exponentially high. Needless to say, for factors of safety such as 3.0, the company could be staring down at losses. So we need to understand that the factor of safety, though it is influencing the cost directly, it needs to be taken out of the influence by putting in its place the design for life, which would help us to understand the warranty requirements of the customer and align towards that. What we see day in and day out in these 7 factors are nothing but the tip of the iceberg. When we go deeper, we see that serviceability costs, warranty issues, recalls, maintenance costs, inventory costs, consumables used in our organization to produce the products or at the customer end, and last but not the least, the customer loyalty. These are the cost influence factors which are hidden and nothing but below the sea level, below the water level, the lower portion of the iceberg. While we see the tip of the iceberg that remains submerged is a lot more. And this is exactly what happens in an organization. So unless we take into considerations the direct costs or the explicit costs and the hidden costs together, the design for cost objectives would never be met. If we look at the influence of each and every input that comes in a product development, starting with design, selection of materials, labor, overhead costs, and so on and so forth, if we look at these primary factors that influence the cost, we see that 70% of the influence on the cost comes from product design. 50% is the material cost, 20% is its influencing factor. 5% is the influencing factor of labor, and 5% is for the overhead. If we look at this influence analysis, if we were to come up with a methodology or a mechanism to reduce cost, we need to look at no other place other than design, because significant influence of 70% or over comes from design. The cost considerations in design should be target-oriented, should be quantifiable, it should have a fine balance between the cost of precision versus the cost of poor quality, and they should be measurable. While addressing costs, the risks and the benefits associated with this exercise, needless to say, go along with it. So the cost considerations need to take into account the risk and the benefit. For example, Toyota had a recall in the 2009-2010 timeframe for an accelerator pedal in many of its car lines. This came directly as a result of standardization of a product across multiple lines, leading to a cost benefit associated with the risk that if you recall in one product or a car line, you end up recalling the other car lines as well. So we need to take into consideration the cost, risk, and the benefits in even scale, and then take the decision further on. The design for cost, when we are taking this into consideration as a design engineer, we should have least number of parts in the assembly, least number of machining operations per part, least cost material, just adequate factor of safety for assured life. The word just is put before the adequate factor of safety to signify a cause that we cannot go overboard when it comes to selection of factor of safety, and it has to be driven by the assured life considerations as compared to anything else. Maximizing the tolerance for meeting the DFQ targets and maximizing the yield from existing manufacturing lines. These are some of the attributes that need to be checked at the design stage if we were to come up with least cost designs at the first time right exercise. The common myths typically taking place in any organization is it is cheaper to produce simple parts and then assemble them than to produce a single complex part. Second, the assembly cost more than offsets the complex part cost. These common myths need to be removed because they are no truthful as compared to reality. Take this example on a design for cost. If you look at the single part design, there are many sheet bending operations in the first part, which is the one part design, while the two part design, the components are easy to manufacture by themselves. So the two part design seems to be more healthier cost-wise as compared to the single part design on account of its complexity. Now let us take a look at the cost comparison. The setup cost, the processing cost, the material cost, the piece part cost, the tooling costs, the total manufacturing costs, the assembly cost if it is associated with the two-part design, and the overall cost. When we take it and summarize it, we see that the two simple parts to manufacture increases the overall cost by over 41%. In other words, the one part design could be a cheaper alternative in spite of its complexity in design in terms of its processing as compared to the two-part simple pieces design. So if design for manufacture and design for assembly and concurrent engineering practices, by conversing with the manufacturing team members, the inspection people, the integration people, or the assembly people, if we take them into consideration, as shown in this graph, if there were no DFM and A analysis, 100% would be the cost index. There would be a 20% savings if we were to do a redesign with DFM and A. Add to it another 20% if it's going to be a new product development and not an existing product. Add to it another 40% savings in terms of relative cost index. Please remember, this is relative cost index. If we include DFM and A and the concurrent engineering practices, the overall cost comes down to 20% of the cost of not having done DFM and A. This is significant change. So the simple steps in DFM and A comprises of taking the design concept, addressing the design for assembly issues, selection of the materials and the processes, and the early cost estimation. This is exactly where the difference starts. And then coming up with alternatives before choosing the best design concept, applying the design for manufacture checklists, and then signing off for prototype development, and then for production. So popular 3D CAD softwares today have the capabilities to do a cost estimation by design. As the design evolves, as more and more features are being put on the single part, the overall cost implication keeps coming as a dashboard as the design progresses. So in other words, if a cost target is given to the designer and the incremental costs are provided in terms of a template, then it is easy for us to see that the cost estimation would come depending on the prevailing prices as reflected on the template. If the template changes or gets updated periodically, then the costs would vary for the same design as compared to the design cost that the same part encountered some time ago. So cost at every step of the design process makes it conscious for the designer to look at alternatives and give the choice to manufacturing in terms of cost versus feature benefits. The same applies to machine component costing as well. Herein, you can also look at the material removal rates and include the cycle time as shown in the next slide. The manufacturing time estimation, as shown over here, helps us to optimize the cycle time for manufacturing even at the design stage. More the complexity, the higher the time it takes, and lesser the profitability because the cost keeps going up. So capturing the manufacturing costs could be done for sheet metal, could be done for welded constructions like in fabricated housings for gearboxes, the plastic parts, milled, drilled, turned, and a combination of these operations. When put together, the persons who are working in design can capture the manufacturing costs and provide a dashboard of the costs associated with a particular design. So if a cost target is provided to the design department, the bang for the buck comes in when the design department sits along with manufacturing, inspection, and assembly to capture the manufacturing costs in addition to the constraints in the manufacturing so as to ensure that least cost alternatives are evaluated before signing off. In other words, we make an informed decision before signing off. Plastic parts cost estimation is shown over here. More the number of features, the short size is larger, the cost goes up. So at every point of time for alternate materials, the cost estimation comes of use early in the design stages. So customizing the costs per company processes is another thing that can be done, and it should be done. For example, painting could be a non-manufacturing cost, anodizing, heat treatment, inspection, milling, drilling, water jet machining, laser machining, plasma cutting, or any other process can be added. For example, packaging and transportation can be added to the overall operation cost so that the total cost can be segmented into the cost drivers, and the dashboard becomes visible as to which are the cost drivers that we need to understand and address before achieving milestones in design for cost. The stock material inclusion helps designs to suit available raw material stock in the inventory. This helps us to bring the inventory costs down as well. The advantage more than that would be avoiding scrap generation and wastage at the design stage. This is a single most important aspect of design for cost that needs to be integrated into the design process so that the overall cost comes down as a result of so many other things in addition to scrap generation and wastage. So the packaging costs can be brought in for different types of packaging, integrating multiple components together in a single package, so on and so forth, so that the costs are amortized. Next comes the assembly bill of materials. Imagine a bill of materials containing the part cost for every one of them. It helps purchase department to leverage on common parts being used across multiple assemblies, getting the buying power for a larger volume. So the overall per piece cost comes down. A very powerful information indeed for the purchase department, for the sourcing department to arrive at the costs and see whether their cost targets have been met for the least cost designs to be produced and to stay competitive in the marketplace. Then comes costing per quantity, the discounting that can be done for larger quantities, and then renting a shop floor in contract manufacturing like many companies which do today, and then looking up at the discount or the markup that we need to give in order to get the order and stay profitable. It gives the heads up information for cost influencing parameters at the design stage itself. The comparative costs between different versions can be compared and then stated. The strength, weakness, and the opportunity and the threat analysis can be done before we select a particular design as an efficacy towards least cost. Next, look at what would be the yield. Give the tolerances for the individual components in the assembly. Look at the measurable specifications as we told earlier in terms of gap, fit, and flush. And you come up with the critical to quality indicators, and you know between the control limits specified on the drawing and the desirable specification limits what our ppm levels are and what are the critical to quality indicators. These are mandatory to get the first time right and to keep monitoring the process only for those DFQ objectives so that consistent quality can be maintained in spite of a lower cost. In other words, lowering a cost does not mean compromise in quality. So the template-driven automation helps us to set up templates for the different products that we manufacture in our shop floor, customer-driven templates, and the values of the currencies in dollars or in Indian rupees or any other currency can be provided here with the corresponding exchange rates, so that the template-driven automation helps even novices who come into the organization to take up the design for cost initiative as a part of the process early in the design stage. In other words, a person who's not knowing the process gets to use it because of a template-driven automation. Then comes the cost reporting, the cost indicators, which are the segments which cost more as compared to the others, so that we judiciously make the design lean and mean so that the lowest cost alternatives and designs have been exploited before signing off on a particular design. These cost reporting can be updated and should be updated every week or every when the costing template goes through a change in terms of raw material costs, finished product costs, machining costs, so on and so forth. So the checklist for low-cost designs starts with providing the manufacturing and the sales department alternate designs with their associated costs. So some could be low-cost designs, some could be expensive designs, depending on the features that we have integrated into the product. Modular designs with differential costs help sales and marketing team in organizations to empower their customers to choose the design by choice, making an informed decision once alternate designs have been provided. This also ensures that the RFQ conversion to order increases exponentially because now the customer has a choice to decide which one he wants to go with. Material cost validation by design is another thing that we need to do early up in the design process by doing the DFC analysis. Subsequently, do a cost contributor analysis, both explicit and hidden, and try and reduce, if not eliminate, these cost contributors, especially the significant ones. The manufacturing cycle time optimization by design, as we had shown earlier, would help manufacturing teams come up with better manufacturing processes so that their overall cycle time can be reduced and they can concentrate on consistent quality. Supply chain integration in the design stage in terms of the design review process, in terms of the process capability, in terms of manufacturability, and so on and so forth, helps compress the design cycle time so that the first time right becomes a reality. A strength, weakness, opportunity, and threat analysis based on cost would drive down the cost considerably and help us to make informed decisions as well. The cost report finally provides the reasons for which we chose a particular design with its parts and their associated tolerances as compared to other alternatives. So the benefits of design for costs starts with increased profitability, improved operational efficiency, eliminating costly designs, reducing the input cost in terms of raw material, in terms of processing, in terms of packaging, transportation, so on and so forth, assuring a superior performance while enhancing the product quality consistently and not to cut corners with the product safety by protecting it at the design for cost stage itself. So the benefits are threefold: commercial benefits, legal benefits, and the social and moral benefits driving a business case out of the design for cost initiatives in any organization. So the results of implementing the design for cost in any organization based on service and the response provided by customers can be classified under the cost savings that resulted directly as a result of the implementation, the ease with which the design was done, how the product development costs got reduced, how the design development cycle time got streamlined, how the project line improved, and how resources needed for a project were reduced as a result of the visible dashboard that is coming in terms of utilization of people, in terms of cost, and in terms of time. So if we were to look at the benefits directly of implementing the DFC, this picture shows the responses of a lot of people who have invested in this, their time and efforts to achieve the benefits that their competition cannot. So now when we look back at the design process overview, we see that the dotted lines are getting connected with DFM, the design for manufacture, being an intrinsic part of this process as much as the design for assembly. Now, historically, we have been looking at manufacturing where every manufacturing stage or station tries to reduce their cost. While this may be a good practice, there are situations wherein more expensive designs would lead to an overall lower cost of ownership as compared to a design process wherein these are not considered. So the key characteristics, the process capability, helps us to understand when the processes go off their centrality, how to bring them back so that the yield can be maintained at top levels. The recommended reading, some of them have been used in this presentation, are Mechanical Assemblies, their development, manufacture and role in product development by Daniel Whitney, professor for MIT. I'm reminded of a saying that goes on in the first chapter. In the final analysis, assembly is the moment of truth. Final assembly is the moment of truth. The next book is Product Design for Manufacture and Assembly by Boothroyd, Dewhurst, and Winston Knight. The software used in this presentation are SolidWorks Premium and Segment Tolerance Analysis for intelligent manufacturing and improving yield considerably. We hope you enjoyed this presentation. We would love to hear from you on info@egs.co.in. Visit our websites egsindia.com and egs.co.in regularly to stay in touch with us on similar kinds of presentations on emerging technologies as a part of our endeavors to further the cause of the manufacturing industry. We hope you enjoyed this presentation. Looking forward to hearing from you. Thank you.